Sleuth Rock in the front row. So I'll give you the preamble that doesn't even need to go on the recording. If you've been to any of my talks, I want you to get whatever you need out of this. So interrupt me, ask questions, and particularly on this one, this topic is so big, we're actually I'm going to give you the choice of how we direct this. So you can lead me down a path, we can work through slides, doesn't really matter. I want you to get what you think you want out of this. And so I'll do my best to answer your questions and stuff like that. And that doesn't really need to be on the recording, but it just kicked in, so we're going to kick off. So the stuff for this, if you want to follow along, it's up on my GitHub, and instead of making a short URL or whatever, I just told you where it's living there. So this is if you want to go grab the commands that I'm running. There is a version of this deck, but it's not working. So I do this talk for clients at work, and our standard is Google Docs. And so all I did was, for this GitHub, was I just pulled down, I don't know why the HDMI keeps going to sleep. We'll try and be on top of that. Anyways, all I did was use the download button from Google Docs, and the Impress was broken. So this version's obviously fixed, and I will push it up when we get that far. So we're here to talk about containers, but not these containers, these ones. So your container journey is often kind of fraught with peril, and I found a clip online that has nothing to do with containers, but I thought this really reminds me of my journey with containers. So I started out, and I heard containers are easy, right? But found out I was going in the wrong direction, was a little confused. So I turn around, and I think I'm going the right direction, and everything's happy, and I run into another hurdle. That's okay. I'll just follow it down the rabbit hole, and I'm going to go full steam ahead, right? Until I ran into some docs that indicated that I'd actually been holding it wrong. And so I thought, nuts to this, I'm just going to continue doing things my own way. I'm experienced at this point. I'm 2 years in, and then I get bit by a snake. So hopefully I can help you avoid some of these things. So this talk is really about how containers are not as easy as you think they are. We're talking from a Linux administrator's standpoint, specifically because we're not talking about like, oh, it's really easy to get an application up and running. It's, okay, you've got an application running, you depend on it. What happens if it doesn't do what you like? It doesn't have any tooling in it except for the application. What do you do with it? And in order to really debug a container appropriately, you actually have to understand how a container works from a Linux point of view. So I like to say containers are easy. They're easy like doing a curl sudo bash, like completely easy, right? Anybody can get a container up and running, but you probably don't want to just do that. So some of the things we could talk about, CGroups, Linux capabilities, and namespaces. I said could because I'm actually going to ask you for your input. But before we start, there's just a couple of 3 terms that I want you'll see in this presentation that I just want you to be aware of. So in Kubernetes, a lot of people come to this because they want to talk about containers and Kubernetes and orchestration or whatever. We're talking about Linux namespaces, not the namespaces from Kubernetes. You'll see an abbreviation here for OCP. This is OpenShift. It's Red Hat's version of Kubernetes. So just that. And the other thing is you'll see DAC as an access control. It's discretionary access control. It's what traditionally Linux uses for file permissions. You don't need to know anything more than that, but you'll see that acronym. So time for your participation. I want to know some stuff about you guys so that I can help direct the talk. Am I going to talk high at you? Am I going to talk low level with you? What are we going to talk about? That's the sort of stuff that I would like to get your input on. So we've got a live poll here. Ideally, when we get to the next one, when I ask you, what you want me to talk about. Only pick 3. It's multiple choice, you can pick 3, but I'd like to find out where my audience is on the spectrum here. So if you need the QR code, I'll put it back up here, or the short URL. Of course, that was not the right thing to tab over to. So we'll get there, I promise. There it is. So if you need that, that would be appreciated. And again, this is a choose your own adventure. Take me any direction you want, or give me dealer's choice and I'll just run you through what I think, because maybe you don't even know what it is you'd like to find out about. We've got some really experienced people. Most of the time, I either get a ton of goat, or like, I get most people saying like I've done a lot of reading, and they really haven't, but that's less embarrassing than I've just heard about it. So most of the people fall into those 2 categories. Okay, this is interesting. All right, so we are going to go to the next one here. Now that I got them. So we've got a mix between kind of new and lots of people that are using it. So that's interesting. So what do we want to talk about? This will be interesting. And if you want to throw out something that isn't on here, we can absolutely have a chat about it. So my day job is container architect at Red Hat, and so we may not have slides for it, but we can absolutely have a conversation about it. So if you're interested in something that I'm not proposing, just means you don't have anything fun to look up here. My goodness. All right, so not very many people interested in permissions. That's interesting. Host names, constraints, okay, that's good. Yeah, this one, the networking one, this one can be quite popular because there's applications for how you can just use the network part of a container across your Linux desktop without actually standing up a container infrastructure. So for example, I have a website that I go to, and I have to turn off like ad blocking and a bunch of stuff like that. And so what I do is I actually just create a Linux namespace, and I launch Firefox in there. And inside that namespace has just different networking settings so that it bypasses all of the ad blocking and stuff like that, as opposed to some other way that you could handle it. All right. So it looks like we're going to talk about resource constraints first. So let's see. Well, fortunately, that's actually the next one right on the list, so that makes my life easy. So CGroups are what are actually going to do the resource constraints. So they stand for control groups. So I'll make a disclaimer here. We're going to be talking about CGroups version 1 because that is the most widely deployed currently in the enterprise. CGroups 2 has been out for a long time. Fedora's migrated it to it. Proper rel has it available if you turn it on, but it's not on by default. Ubuntu uses CGroups version 2 in the most latest release and so on. But we're going to be talking about 1 because that's the most widely deployed. So in the context of OpenShift or Kubernetes, they're going to be used interchangeably. So what I'm doing is, if you're coming at this from a container orchestration standpoint, I'm just going to tell you like why you care about this from a container orchestration standpoint. So there's this idea of a request and a limit inside of container orchestration, and what this does is says like, okay, I'm going to deploy a container, okay, and the scheduler then says, okay, I could throw it on any one of these nodes. How do I make some decision? So a request is, I need this amount of CPU or this amount of memory as a bare minimum, and so the scheduler will look around and try and find a slot for you. But you can ultimately put in a limit which says this application can burst up to whatever amount of resources that you need in order to function appropriately for like high loads. This projector hates me today. Didn't have this problem in the last time. Anyways, doesn't matter. We'll soldier on. So Kubernetes and OpenShift have this idea of requests and limits. How does it achieve this? Well, it works with CGroups, and what CGroups do is essentially it takes a PID, makes an internal group out of it, and then applies permission to the group. So CGroups actually control access to hardware, not just hard drives. And so in an orchestration context, C groups are these requests and limits. So that's what's happening here. So why should you care? Well, wow, my goodness. I need to bring my own projector. So I apologize. I like graphics and stuff like that. Essentially, C groups controls your access to all of the hardware on your system at some level. Okay, so the kernel is responsible for all of the hardware interactions that happen, and most people are aware of that. Like the drivers live there and all that sort of stuff. And C groups are what helps the system decide how much RAM or how much CPU or things like that the system can use per process. Okay. So this is really great when all things work together, right? Normally, so what happens, you're using C groups whether you use it or not. A default Linux install, doesn't matter if it's your desktop or a server, it makes one group and just puts everything in one group. And so nobody knows they're using C groups because you got one. And so this works okay. And what developers have implemented in order to help with this is like, if you have some sort of resource contention, the out-of-memory killer comes and starts whacking things, right? And just destroying your processes if it decides to do that. And that's okay, right? It's meant as a last line of defense. But realistically, the system should be architected to be using C groups, okay? And this is not a containers thing. This is just like a general administration kind of process. C groups are implemented in containers so that you can run all of these things without worrying about them stepping on each other and worrying that the out-of-memory killer is just going to go start whacking your processes. So how does this work? So there's like I said, kernel controls this sort of stuff, and it works in a system of shares. So it gets a little hinky when you're trying to conceptualize this at first. It's really hard to describe. When I pull up a terminal and, you know, fingers crossed the demo gods will actually roll with me because I'm going to do it live, it'll make a lot more sense. But essentially, the way that C groups works is it's a weighted affair. So by default, every process is assigned a number 1024. It means literally nothing. That's just what they chose. And so what that means is if everything has a number of 1024, they all have equal access to the hardware, right? And so that's why the out-of-memory killer just randomly whacks things, because everything's assigned kind of the same level of priority, okay? So this idea of shares and weighting is if I wanted to give something a higher priority, sort of like nice but not really, I just change the number that process gets. And I have a slide on this and we'll see. So C groups ends up controlling a lot for you here. Are you gonna work for me? Click. Well, there we go. So there are 4 main tasks of C groups, and some of them sound kind of similar, but they are kind of different. So the first thing, come on and press, leaving me out to dry. So it does resource limiting, okay? So this is what allows you to go in and do things like acceptable amounts of CPU or RAM that a process can use. And this is different than prioritization. So prioritization is if everything has the same amount, like if for example, I've set no limits at all in terms of the amount of RAM or CPU that I can grab, well, the next thing that it defaults to is, okay, who should I rank higher or lower? And so C groups controls like a process hierarchy to determine if you've got resource contention and there's nothing defined in terms of how much each process should get, well, next I fall back to prioritization. It also does accounting. So this is turned off by default on most distributions, but essentially accounting, what you can do is it looks almost exactly like top, but it'll break down by process and then threads inside the process, how much CPU, RAM, disk I/O, all of that kind of stuff, everything is using. And so you can turn on accounting on the fly, like you don't have to reboot your box or anything like that, and to turn on accounting by the fly, and you can do some extra debugging, and it's useful. And then it does process control. This is something that advanced people might use. It's not used in Kubernetes, and people get confused by this. There's this thing called Freezer. It's been built into the kernel a long time, like 2006. What Freezer allows you to do is to stop a process, it completely freezes a process. You can pick that process up and drop it on another computer and turn it on. And that's it. That's what Freezer does. So what C groups helps you with this, is CGroups is what says, okay, we're going to stop. It's kind of similar if people are familiar with vMotion in VMware, where it's literally going to copy RAM from your VM to a new host, and that's kind of how it slides things around. That's kind of what Freezer is doing. And so CGroups is what facilitates that. It essentially locks the access to the hardware exactly as it is. So it doesn't delete the system RAM or anything like that, like the memory or what kind of process it's doing. It literally just puts a stop to it. It takes account of what's there, and then you can pick it up and move it somewhere else. Big clients of ours do this. This is not what happens in containers. What happens in like a container orchestration is I want to move the container. What actually is happening is container A is your current container, and container B needs to move somewhere else. Container A continues to hold traffic until the system has confirmed that container B is up and able to handle traffic. Then it spins this one down and transitions the traffic over. So containers actually don't move around in the cluster. What happens is one spins down, one spins up, and there's some control over when that happens. So the last thing that happens, and this I don't see very many graybeards in here or old timers, but back in the day when you first installed Linux, there was something called mknod, and nowadays we have udev, and we've got a bunch of these things that will help you determine, like, did I plug in a USB device, where are my disks, and that sort of stuff. This is just a picture of like /dev, makenode, or make, and I don't know, I call it makenode. I don't, because it's for making a node, but anyways. Everything got populated by makenode, and what that meant was that when you installed the system, you actually had to tell it, I have this device. This device lives on this spot. This is how you access this device. This still exists in the Linux kernel today, and it is very important because it is a security hole if you don't pay attention to it. So the people that know that this exists can exploit this if it's not protected properly, because it allows you to create a device and write directly to that device, whether it's a block device or something else. So this is just a little aside. CGroups controls this as well. In container world, you don't have to worry about that, because I have yet to see a container that, absent of some sort of bug or something like that, like exploit, they take care of that very well. So what's happening in CGroups? Wow, this is not awesome. So essentially, CGroups is a hierarchy, CGroups version 1. If you looked up version 2, the hierarchy is going to look a little bit different. But essentially, you start up here with a group, and then groups are broken down into memory, disk I/O, and CPU as a general heading. And then you can create groups underneath each one of these headings. So like, just because I have a C group called web services doesn't mean it automatically gets one in memory, disk, and CPU. You can have just one or the other, or you can have a mix and match. So I create a group, and then I assign a PID into the group. That's what's happening here. So in this demonstration, PID 1 is actually living inside the web services group for memory, but it's living in the data storage group for disk I/O, and it's living in the data processing group for CPU, because you can do that, right? There's no, because you're assigning the PID into different groups, it doesn't, like, just because I assign a PID to one group doesn't mean it automatically gets added to another group. So there's no relation between the groups at all. So we were talking about CPU time. Wow, this is not going to translate very well. So essentially, what you're looking at here is inside of a Kubernetes distribution. This is how a default CGroups is set up. So you have one group at the top. Like I said, every Linux distribution has a group, root or slash, and it's represented just like a file system hierarchy. So you have slash, and then over here it says system slice. And under a system slice, this is things like cronny and SSH and a bunch of stuff like live under this one. Okay. Then you've got the init group, and systemd is the only thing that lives in the init group. And then over here, this is the Kubernetes slice, and the Kubernetes slice is broken off into two different things. You don't need to know how this breaks down, but it's just to give you an idea. Like, it follows like the file system hierarchy, and you can actually go in and ls these directories and like see this out. Or they actually even have lscgs, which will do, it's an ls for CGroups. I'm going to stop here First of all, am I giving you information that's kind of interesting? Should I, like, I'm getting a couple of thumbs up here. We like how this is going so far. I really apologize for this projector. I don't know what's going on, but we'll soldier on. So anyways, this is step one of the shares. When I was telling you about how, like, there's math involved with the shares, okay, everything defaults to 1024. So your very first root group gets 1024, okay? And so and these three groups that get created in Kubernetes also get a default of 1024. And then I create new groups under here, and they get defaults of 1024, okay? So everything gets, just by default, that's just the number somebody, okay, that sounds good. But what actually happens when we're doing some math is that when you're trying to determine how many CPU shares or like what percentage of CPU time you're getting, you actually end up with a system. So we had, across the group, we had three higher level groups. We had the system group, we had the init group, and we got the cube group, okay? Each one of them have 1024. This math is really easy. You got three groups, well, that's 33%, okay? So they all get equal weighting. And what this means is that if they're all firing at the same time, the system's going to limit each one of them to 33% of the resources on the system, if they're all firing at the same time. If they're not firing at the same time, the system lets them run roughshod unless you tell it otherwise. It's like that idea of the minimum amount that I want and the maximum burstable amount. That applies at this level too. But by default, the maximum burstable amount is not set so that you're not handicapping your system. And again, this applies to all Linux systems, not just containers and Kubernetes. So I'm going to try and give you a demo. I'm going to show you here if my graphic kind of kindly would show up. So what I'm going to eventually do, are you going to work at all? There we go. Okay. So this is what we're going to try and achieve. So I'm going to create a user group, and I'm going to assign it 2048 just to make it different. So I'm going to have three users, user 1, 2, and 3, and I'm going to assign one of them 2048, which is going to give them half of the resources on the system. Then I'm going to fire up a bunch of systems, and hopefully I don't bring my laptop down. And you'll see in top how at first all of the systems will kind of bounce all over the place like top does. And then when I apply the C groups, what's going to happen is that one of them is going to peg roughly at 50%. Like because it's a weighting and not a statistical percentage, it might bounce between 41 and 51%. Like it'll bounce around in that vicinity depending on how things are kind of orientated. So the first thing so this is the part where if you wanted to follow along, there are some stuff inside of that GitHub repository that will actually have the commands for you. And I'm just going to turn on my VM and move it over. So just give me a quick second, because apparently it crashed when I put it to sleep. And this is why you never do live demos, but it also makes things interesting, right? There we go. All right, turn on. We're going to move this over here. Go like this. We'll make it really big because why not? And I'm using a super secure password, I swear, for this VM that never runs unless I do demos. So these are just, I'm not actually going to run the shell scripts. I just called them shell scripts because it's easier to do things. So we're going to work with the C groups one. So this is essentially the set of commands that we're going to be running here to set things up. So remember how I said that C groups are just a file system hierarchy. They can live literally anywhere on the system, and I'm going to demonstrate that right now. So I'm going to create this directory, and then I'm going to mount C groups into that directory. And so there are three different types of C groups that I'm going to be mounting. I'm going to be mounting the CPU shares, and I'm going to be mounting memory, and I'm going to mount CPU sets, but we're not going to use them in this demo, but I'm just going to do that anyways. So. Probably should have grabbed them all at the same time, because that makes a better demo. Because you guys don't care to see me type. I wouldn't anyways, that's kind of boring. All right, So if I look at so right now they're just directories, but since I mounted stuff into them, I now have all of the, I basically just moved my C group directory from wherever it lives by default here for the purposes of demonstration, right? And these are all just flat files, just like everything else inside of Linux system. So like if I looked at tasks, right now there's nothing in tasks. So tasks is where your PID is gonna live. So I'm gonna start creating some C groups, then I'm gonna assign a PID into them, and you'll see how this all kind of comes together in the end. So I'm gonna create my user. So if I'm in, and again, these are not actual users. I'm using users because the people that I normally talk to grok users much better than trying to sort around groups. So I just named the groups I called the groups users because it makes life easier trying to explain things to people sometimes. So I'm going to do user 1, user 2, user 3. Right, so now I've got these users inside of my CPU. And I'm going to do, so now my groups exist. So the C group existed because I mounted it there. Now I created a directory, so those users now exist. And the next thing that you do is you literally just start echoing things into the CPU shares. So the CPU shares, like I said, are where the weighting is happening. So if I'm going to echo 2048 into, I think I said, I don't even remember which user I said I was doing this with, but I guess it doesn't really matter. So we're going to just do user 1. Oh, well, yes, that would make the math much easier. And then I'm going to do 2048. Thank you. It would illustrate the point, just not nearly as cleanly doing like someone at home trying to figure out what's happening with the math. So, right, so. And then I'm going to do user 2 and 3 at 1024 because easy math, as long as I can type. And again, all these commands are up on the GitHub. And sometimes when I do this for extenuating circumstances, I do 512, 768, just some random numbers, right? And so I need to open up a couple terminals now just to make my life easier. You don't need to be able to see what's happening. I'm just going to generate load on the VM by logging in on a different terminal here. So cat dev urandom into dev null, and then SHA 256 sum. And so that should start generating me some. So I'm generating some load here. Wow, that is the wrong direction. I have to make this smaller so that. So right now you can see I've started something here. I have a process. It's basically burning all of my CPU because this, again, easy math. I'm making this VM should only have one CPU in it to make things easier, right? So I have a process running, but it's unconfined because I started a PID and it's not existing in any of those groups right now. So in this case, I'm going to grab that PID. So it looks like 1380, and I'm going to add that PID into, I don't know, CPU1, I guess. So if I do echo 1380 into CPU, probably user, that's better. And then tasks. So I should now have a task with a PID in it. So now I'm going to start opening up some more terminals here, and I'm going to put PIDs into different things. So I'm running the exact same command, and so I should be generating 3 different processes that are going to be running at 100%. That's ultimately what the goal here is. And if this stuff is getting like a little bit boring, like you're like, oh, okay, yeah, I get I trust the fact that, you know what, this is actually going to work. We can skip along as we move through these things. So I'm going to do another one. And one more. So if I look at top right now you'll see that 1380 has very little of the CPU utilization, even though I told it should have 50%, because everybody else is unconstrained. So the unconstrained processes literally are going to run roughshod across your system. So I know it's hard to see, but essentially the other processes that I've just spawned off here are eating all of the CPU, and the one that I've constrained is eating like 3%. And that's expected until I start constraining processes. So I'm going to take a poll here and say, who wants me to continue with this style of demonstration, or you get the point? Because like, I don't want to belabor you. Like, watching somebody type is legitimately boring. So I can do this. It's fine. You want me to move on to more like conceptual things or have questions, you can do that too. Do you want me to finish this part of the demo and move on? What would you guys like? Okay. Who wants me to continue typing because you're bored and like to sleep? That's a good way to phrase it. Nobody put their hand up. But seriously, who wants me to like just finish off this demo? Like, do you like this style where you're seeing this in action, or do you just want me to talk about it? I see a couple of nods. Okay, who wants me to move on? I'll do this. The move on, have it. If we want to do more demos later, we can absolutely do that as we move on. So the point of this is that just you can rearrange things by, you know, I'm just going to stop my VM quickly because otherwise I'm just burning cycles for nothing. So the point of this is by echoing different things into the directory wherever it lives. Like, I created it there for ease of use instead of that long, weird place that it lives in the kernel normally. You can start controlling CPU and disk, and all of those sorts of things are controlled in the same process, in the same kind of facility. And so the only other thing that I wanted to draw your attention to is, like, you saw me create the CGroups by hand. If you do this and you reboot your box in the way that I did it, they would go away, okay, because I just did a temporary mount. You can use systemd to do this, and inside of your unit file, there's a keyword called slice, and then you just call your slice whatever it is you want to call your slice. I called it awesome slice. When I do extended demos, I have different slices, and we go into like the audit mode, and you can see how everything's working, but we're not going to do that because that's boring. All right. There were some people that wanted to talk about permissions and like how that works. So I'm going to skip through this pretty quickly. I'm not going to give you the whole thing. But as we know, we've seen how security can be very difficult just across the board. Like, just take passwords. Passwords are terrible. Users don't understand how passwords work. Just like people running containers don't understand how the security works in there. So like, when you go to set your password, this is pretty much everybody's experience ever. Right? You go in and you're like, yeah, I can do this. I'm going to pull out my phone. Sure, password, done. Let's get on with my business, right? And then, turns out that's not the password you need to log in with. So you're going to reset your password. And you try again. And of course you fail. And password security is hard for the average. It's hard for everybody, unless you have a password manager to do it for you. And this is how I feel like what happened with containers. Like, people just started smashing on things like to get the permissions to work, and it works magically. So containers are hard, permissions are difficult. We're going to skip through a bunch of this stuff in the interest of time. So you need to do stuff, right? You don't want to run containers as root. So how do you do that? A regular user permission might not be enough. You might need some elevated stuff. Like, you need to think about things like I can't run sudo, so I can't have a way to escalate privileges, and people thought about this and broke this down into, at last count, there's 42 or 45 things called capabilities. So what they did was they looked at all of the things that a user does on a system and like tried to categorize them so that you can fine grain, like, you can do this, but you can't do this. You can read this, but you can't write this. You can write to this if a file exists already, but you can't create a file. Like it's very granularly broken out, and that's what happens inside of Linux capabilities. I personally think that we do a terrible job naming things because we have so many naming collisions. Like when you say, oh yeah, like the capabilities of a system, and people are like, oh well, it's got 10 CPUs and 100 gigs of RAM. Like no, that's not what I'm talking about. So traditionally, we have, in Unix, we have DACs, or discretionary access control. So these are things like users in groups. We've got set UID and set GID and all those sorts of things. And those are good, especially the set UID and set GID, except when a programmer does a terrible job with this, especially the set GID or set UID. These are problematic. So the password has been beaten to death, and it's set as a set UID. What this does. What it does is it says, you're allowed to run this process as whatever user owns that binary. Okay, so the password file has to be able to write to privileged areas in the system like shadow and places like that in order for you to change your password. But they don't want to give people root access just to change your password, so they applied the set UID to the password utility. So you type password, and you can change your password, and it writes all of those places. That has been audited, 5 ways from Sunday. But a lot of the stuff that ends up implementing this hasn't. And so the powers that be sat down and thought, well, how do we get around this? Well, capabilities breaks out that permission. So instead of just like you run everything as root because root owns that file, now capabilities allows you to like split these out super granularly. So yeah, as of 5.15, there was 40. There is more than that now. We don't really care very much, but things like chown, network administrator, system administrator, all of these sorts of things are broken out as part of the permissions process. And why I didn't want to skip this slide, even though a few of you didn't want to talk about permissions, is because if we talk about user namespaces and how things stay separate from each other, it's really important to know the capabilities are tied to a user namespace. So just like everything else on Linux, like the CGroups, everybody's using a namespace and you don't know it. It's just one namespace for everything. And what that means is, if you don't know how this works, all of the permissions from your system get inherited into the container because it's all in the same namespace. So the same thing with capabilities. Capabilities are on your system, you're using them, you don't know it. They've just changed the way that your system is running. This is important to know because when you spin up a container, and it has been poorly orchestrated. So this is not on you, this is on the person who designed the container, whoever containers you're ingesting. But if they did a bad job, the permissions will be inherited, and that's why you hear things about like people being able to jump out of a container or some privilege escalation from inside the container when we have this supposed like sandboxing, right? So it's because there was some flaw in the way that they set up these things because they either didn't understand how the inheritance works or whatever. So we're not going to cover too much about how inheritance works because that's kind of boring unless you really, really want to know about it. So I'm actually just kind of skip over these. There's a bunch of capability sets, which is a way to group capabilities together. What you need to know here is that there's what's called effective and there's permitted. So effective is like, this is what's running right now as this process can do blah. Permitted means like, this process may need to escalate its privileges from time to time, but probably shouldn't run with these elevated privileges. So it's kind of like that burstable capacity. It's like, you should normally run with these set of privileges, but every once in a while you might need to do this thing, and we don't want human intervention. So we put this on the permitted list, and the process itself can say, hey, I'm ready to do that thing that you said I could do now. You need to know about this in terms of keeping things tight here. If you want to see what your capabilities are, there's a program called get pcaps, and then $$ just says like my current session. So there's two different things you'll see. You'll see you don't even have to care about any of this. It'll just enumerate. On some distributions, it'll enumerate. On some distributions, instead of enumerating everything, there'll be a space, and that means literally I can do everything. And it depends on your distribution, both server and otherwise, which one of those you'll see. So let's go back to my, right. So are we relatively happy with the explanation of how constraints work? Should I make a summation of that? Do we want to move on? How are we feeling with that? Because like most of you wanted to know about that. Thumbs up, thumbs down, in the middle. Okay, I got a couple of thumbs up. All right. So it looks like we want to hop over to networking. So let's do that. So networking is a big one. And I'm actually going to skip through tons of slides because it's usually at the end because it's so big. But we're time constrained, so let's see. We don't care about this. Mount spaces are interesting to talk about. Maybe we'll get time to that. Especially because if you want to know how you can run a different distribution on top of a distribution inside of a container, the mounts are what helps you with that. Process namespaces, we'll come back to that. Hopefully I'm not putting anybody to sleep. I normally dance and sing a little more than I'm doing right now, but he said, do with what you got. All right, we're going to take a brief detour here into UTS namespace. It stands for Unix Time System. That's not what it does. I don't know why I know why. There's legacy behind the idea of the Unix time system. So back when Unix was a thing, what happened was you only had a certain amount of time on the system, and it had to know how to kick you off, other than by user, because everybody logged in the same user, more or less. So they had this idea of like, okay, I needed to run a process, and I needed a way to identify the process, and we weren't identifying the process by user because way back then everybody logged in as root. So they developed this idea of what we now call host names, right? How we identify a computer. They used Unix time sharing as the way to apply a label to a set of things that was happening for, maybe the math people needed to run some computation on the mainframe, and then the physics people or whatever. They did this inside of the UTS namespace. So this is actually, to this day, the UTS namespace is how you have a host name on your system. There's a little bit of nuance there because you can actually set it in the kernel, but as a general rule, this is where your host names come from. This is important to understand before we get to networking because, well, lots of things rely on a host name. So we're just going to skip through this pretty quickly, but we like host names as humans. That's really important. And some processes actually want a host name. Like they will complain if you don't have a appropriate host name. Like a simple example is like, for example, if you issue an SSL cert and it doesn't match the host name, it freaks out at you. So ultimately, the UTS namespace is how you end up having different host names for containers. And why this is important, largely, it's not because we actually care about the name of the container. It's like when you go to get logs, how do you determine which container this log came from, especially if you're running 17 applications that are all running Java and you need to figure out which container this is coming from. We use a host name. We call it a container name, but it's actually just the host name in the container. And the logs will identify themselves with their host name. And so that's super important when you're dealing with containers. Yeah, so we don't care tons about this. I'm not even going to go through the demo, but essentially the time sharing controls things like the set host name command. It runs there's a clone command that we don't care about, and it also controls uname. Most of those things that people will have bumped into at some point in your Linux journey, unless you started last year, because a bunch of these things are slowly being replaced by systemd for good or for ill. Come on. All right. We're not going to try this because I'm not going to demonstrate it. But essentially, all I do is I log in. I create a container, and it normally inherits, by default, the container inherits your host name. So you log into a container, and there's no way that you know that it's a container other than the fact that it's got a different set of processes on it. So when you first create a container, you have to set a host name. Now, this is done by Docker, by Podman, whatever, by default. Okay, it's done for you. But if you followed if you actually debugged the process, you would actually see it going in there and setting the host name. So all this does is it shows you like, hey, I'm setting a host name. There's like a tiny caveat here where systemd actually uses a socket to set your host name. The only reason this matters is because the socket's not controlled by the UTS namespace. And so if you actually go into a container and use systemd, because you're a masochist and put systemd in a container, and try to change the host name, what will happen is you actually change the host name of the host the container is running on. Because it talks to the socket, and the socket is running on the host, and then you type host name in the container, and the container just has the same host name, and you're like, what's going on? I kind of stumbled over that one by accident during a live demo. So yeah, it's just word to the wise, don't do that. So now we'll skip ahead to the networking stuff. It's important to understand, host names in relations to that. So if you want to try all this stuff on your own, like I said, the commands are out there and it's pretty easy. I also have written some articles about this. But the network namespace. So this one is by far the most debugged. If something's going wrong in your container, 99% of the time, what you want to do is get in and do a TCP dump or something. Like usually it's not the application failed and I need to debug the application because it's got logs, or I can spin up an application in a VM or whatever. Like there are ways for you to debug application-specific problems. It's really challenging for you to reproduce network-specific problems somewhere other than where they're happening. And so the reason why this is a big topic and important is because container needs to have its own IP, because at least currently we're all doing routing over Ethernet and the IP protocol. So how do you do that? How do you have something living on the host? So experienced people will know that you can create a network device and then you can create like a virtual network device and you can assign a bunch of IPs to the same thing. But the applications themselves are not going to necessarily know how, like, most of the applications are not bound to an IP. So traffic comes in on 192.168 blah, the application is going to respond. It comes in on 10.10.10 blah, the application will respond. So you don't want that with a container. You want a way to be able to direct traffic at a container, and so they need to have their own IPs for various reasons. We want to talk about that more. Hit me up afterwards because it's long and detailed. And obviously, you don't want to have an impact from the container otherwise. So a practical application for using network namespace outside of containers is that you can establish a VPN tunnel inside of a network namespace. So again, going back to my Firefox example, I watch Nesson for Bruin Sports, which is in Boston, but I live in South Dakota, and they have a region lock on it. Sure, you could like set up a global VPN, but I also just have a script that fires up a network namespace, launches the VPN in that network namespace and launches Firefox, so that, whatever, I often do this, like have it up during work or whatever, and it's just kind of playing in the background, and it doesn't disrupt my regular browser. Like if I was to connect to a VPN, then all of my client stuff breaks because I'm no longer coming from where they expect me to be coming from. So you obviously want to make sure that your containers are not impacting each other, and the way that happens is by using these network namespaces. So they allow you for discrete networking. So you can run as many processes of like OpenVPN or WireGuard as you like, and just apply them to the different namespaces, and that's essentially how that works. So obviously the net namespace controls everything in the networking stack, right down to one of the interesting things that you can do. It's more advanced, but you can actually tag a packet so that your firewall will pick up on that tag and do something specific with it. And that's useful in a larger context, because normally what happens is when a packet leaves your system, it gets tagged with the system stuff, like it gets encapsulated, right? And it gets to the router looks at it and is like, oh, this came from this host. I will apply these set of rules to it. But you can actually, in the network namespace, you can actually apply tagging as they're coming out of the container. So when the firewall receives it, the firewall can look at it and say, I'm going to do something completely different because I know it was coming from this container, even though it came from this physical host. And that's kind of been a step forward for a lot of network control. You still control things with the IP command. So, IP link, IP netns. So the IP command, which is replacing the ifconfig command slowly but surely, actually has built-in facility for talking directly to the network namespace, which makes it like really easy to script and stuff like that. In the old days, you had to do a bunch of janky, not janky, but involved things, and now it's literally just built into the network command itself. If you're trying to connect, so if you need your containers to just go out and talk to the world, you don't need to do anything else. If they need to be able to talk to each other, you need a virtual switch, because essentially networking didn't change just because we invented containers. And you'll see this as we go through. I'm not going to do the demo because I think we're short on time in terms of that. But you can do things like segregate DHCP and DNS and VMs and all that kind of stuff. Like you can work to segregate this stuff so even broadcast traffic is only targeted at specific things, and that can be very useful. Questions? I know I'm ripping through this. I'm trying to get to things that you may care about. I hope I'm getting things you care about. So, any questions at this point? I know, it's like a fire hose. Is there a question? No? Okay. So, as part of this, when I give these kind of longer talks and we have a little bit more, I actually walk you through various scenarios. So, one of the things that you do is you create two namespaces. We don't create two containers, we just create the namespaces to keep things simple. And then essentially, networking hasn't changed. You create a point-to-point link between those two. We call it a crossover cable. So it ends up looking something like this. So you call these whatever you like. I call them client and server because during the demo, I actually put DHCP in here. And then I have my container pull its IP from this without affecting the host or anybody else on the network. Because I've literally made a point-to-point link between them. And the way that this happens is you create a virtual Ethernet pair, and then you plug the pairs into the, you just say this side goes into that one, and this side goes into that one, and then they just start communicating as long as they have, as long as one of them has an IP. So, as part of the demo, like I said, normally I end up walking through like, hey, here's how you create the interface and like all of this sort of stuff. But again, I think we all agree that typing is sort of boring. So I'm not going to do that for you. If we want to do a birds of a feather, or if you're interested in chatting about this, we will. But I want to keep this sort of moving along here. But ultimately, one of the things that I do is I end up running a Python web server just so that you can see, like, I can hit this from the container, but I can't hit this from my computer. Even though the computer's running these namespaces, I can't do it because I've created a point-to-point link between the containers. So there's some stuff that you can do, like you can make your host attached to the network namespace, but by default, if you have two namespaces and then you say, you're going to talk only to this one, that communication happens, and there's nothing you can do to sniff that packet unless you craft it such a way as you say, okay, I'm going to elevate this privilege into that namespace. Okay. Why do we care about this? So getting back to the idea of like, I have a container, it's running, I need to be able to reproduce what's happening in the container at a network level right now, and I don't want to restart the container because maybe that ruins my chance at capturing whatever problem that I have. Well, what you can do, once you understand the fact that a container is just inside the network namespace, there is a command that will actually link the PID with what namespace it lives in, and then there's a command called nsenter, namespace enter, and you just enter that namespace, and because you're only entering the network part of the name, essentially your host is adopting the namespace of that network device for that period of time. You still have access to all of the things you have on your host because all you're doing is adopting the network portion of that container. So that's really useful if you need to do TCP dump, if you need to do GDB for like debugging, whatever it is. It's super useful to be able to break this down. And so again, the purpose of this is to hopefully give you little areas of investigation to help you debug these things from the low level, because a developer is going to rebuild, and time and time again, they're like, oh, I'll just rebuild this container with TCP dump, and then they forget to remove it. Or like that container, they remove it, but nobody actually updates the image, or all kinds of stuff. Or they roll out a new container, but it lands on a different host, and then you can't reproduce the problem. So it's really important to understand hey, these are just, you could even break this down and think this is just a folder on my system, and all I'm going to do is like adopt that folder as my new root for this time period, and you can do lots of different things with it. Yeah, so point to point is interesting, but like how do you actually do something useful? So there are a lot of different options, but Red Hat prefers Open vSwitch. There's all kinds of ways to do virtual networking. But essentially, Open vSwitch is exactly what it sounds like. It's a virtual switch. So in this demo, I create an east-west and a central namespace, and I plug all of their ends into the switch, and they can all talk. But my host still can't talk to it until you plug into the virtual vSwitch as well. And so this is how you can either limit communication between containers or extend it, depending on what your purposes are. And so if you take nothing out of this network section other than this, networking did not change. If you want to connect a bunch of computers together, you need to switch. If you just connect two computers together, nothing else can see that. The fundamentals of IP did not change just because we found a new way to install applications. That's the takeaway from the networking stuff. And then we have a big let's try it section because it takes quite a bit of typing to actually set all of that up. Now, when this stuff gets taken care of for you, if you use the appropriate flags and stuff like that, when you spin up a container. Now, most of the time, this is a given, and the system will just automatically give IPs to containers as long as it's set up appropriately. So you don't really have to worry about setting this up by hand. The demo is to show you that it's just bash. I'm literally just typing bash commands, like I type IP netns add this namespace, like, you know, and then you do things like add this network card to this bridge, and it's literally just the same thing that you have done if you've done any network administration ever on a Linux machine. It's the same thing, but it takes a long time to type all of that sort of stuff. So we're not going to do that. And I don't know why it started all over again. So that's the networking stuff. I know that it's a lot, and I talk quickly. If you have questions, please ask. If it's boring, tell me. I will not be offended. I want to give you something. If you want to talk about something else, we can do that too.
You have 4 minutes.
I don't care. But nobody's behind me, so if people stay and you want to listen, I will keep talking. So I'll talk until nobody's here or somebody kicks me out. So, open forum. Otherwise, I guess we're going to move into hating on the projector again. So we did the networking. We talked about how resource constraints work. Process controls. Okay. So this is a combination of 2 different namespaces. The primary one, and we talked about host names, so we knocked that one off the list. So process control happens at the first layer is the PID layer. So you may or may not know that everything inside of Linux gets tied to a process ID. Why are you not? There we go. I'm just changing the slides because instead of flicking back through them, it's just easier for me to do it this way. So everything ends up having an ID associated with it so that the system can track what's going on. Okay, that's pretty standard. The difference is that if you did a PS or you run top or anything like that, you'll see literally everything on your system, and that's bad. Okay, that means that anybody can see any other process, and as I showed you with CGroups, it didn't take elevated privileges. I just needed a PID and a mount point, and I started inserting things. And so you can do a lot with just the information of a PID. So process isolation happens in the PID namespace. You don't want to fire up a container on your host and have the container see all of the things that you are doing. Even if you make a really stellar container, that's still a bad idea. You don't want that level of intrusion. So what ends up happening is when you create a new network namespace, a new PID namespace, what happens is the very first process you run becomes PID 0. So systemd no longer exists in your container. It's no longer, PID 1 or whatever it is. It's whatever process you run first in that namespace. If you're creating it by hand, it will be bash, because that's what happens. Like when you finish typing the create command, it automatically populates a bash shell, or else why would you create a namespace? But when you're creating container, obviously you can tell it, launch this process, not bash, or whatever it is you are trying to do. So when that happens, it can only see from that point forward. So if it launches bash, you'll be able to see everything in the container that runs in that bash shell, and that's probably what you want. But it can't see up the stack. So it can't see anything from behind it. Container isolation requires you to have this idea of a process ID isolation, because you want to be able to ensure that all of your processes will remain unique. If you've ever tried to no one has, I guarantee it. I'm the only crazy person in this room, likely. But you can actually dictate what kind of process ID that your process will have. And if you create one with a process ID that already exists on the system, bad things happen. And so this idea of like, I want to make sure that I keep my container separate, making sure that your process ID